So, how's everyone doing?
Good. How are you doing?
Cold.
Yeah.
So, test week has begun, starting this afternoon. What's on your minds?
I wanted to go over a question on the practice test.
All right. Got my answer key here. Which one is first?
Number 5. When I was going through the work and I was like talking my work, I was just confused how how it's supposed to be 5.972 at the bottom, and then you change it to 6.72. I was just wondering where you got the 6 from.
At the bottom.
Oh,
The masses.
that would be a mistake on my part.
See that?
Alright.
So, thank you for noticing that, because I certainly didn't.
I was like, I don't know where you got it from. Maybe I'm missing something.
I pulled it from nowhere, and that's the problem. So thank you for bringing that to my attention. I must have just gotten, something happened in my brain. I apologize. That should make the answer smaller than what's on screen right now, so sorry about that. Let me recalculate what that should be. So 5.972 E24, that's divided by okay, so this first answer should be then 168,013.2 meters, which would also decrease the final answer by about 2,000. So, the orbital radius should then be about 13 million, and that would make the height above the ground about 6.8 million. Is that better, closer to what you had?
Yeah.
Okay. Thank you for telling me that. I'll have to revise my answer key. Do please call me out on my mistakes when I make them, because if I don't fix them, then that's bad for everybody.
I have a question on 9, because I think, like, there's also a number that I don't really know where it came
Oh,
from.
yeah.
Because you use 0.5, but the rope is attached at 25 centimeters. So I would have expected to use 0.25.
Correct. Now, so this is, for those who are just listening, it's technically a balance beam question, but it's kind of like the flagpole from class. The hinge is here at the corner. And part A is first asking about how much torque just the sign and the mass of the pole create by themselves. Now, so right now, all I'm doing is adding together the clockwise torques. That would include the weight of the sign and also the weight of the flagpole. Both of those forces pull in the same direction on the same side, so they're generating clockwise spinning torque together. So these two torques over here is the weight of the sign, 15 kilograms, positioned 1 meter away from the fulcrum, and this is the weight of the flagpole, whose mass is located in its own center. So this 0.5 is just half the length of the 1 meter long flagpole. And then the 0.25 you mentioned for the rope, that I looked at in part B, figuring out, you know, if this is the total amount of clockwise torque, the rope has to be generating the same amount of counterclockwise torque, and the Y component of the rope at 25 centimeters would need to exert enough force to generate the same amount of torque. So that's where the 0.25 came into it, the way that I did it. So again, that 0.5 is just the location of the pole's center of mass.
So could you just like go off all of the things on this side are gonna be clockwise and that side's gonna be counterclockwise?
If it was a balance beam with two sides, yes. So what's happening here is these two forces both pull in the same direction, but they're on opposite sides. So they generate opposite sign torque. In this case though, the hinge is actually here. So technically every force is on the same side of the hinge, but the forces themselves point in opposite directions. So the two main cases are same direction force, but different sides of the fulcrum, and that generates two different directions of torque. So this side would be clockwise, and this side would be counterclockwise. But here, since they're on the same side, the direction of the force then determines the torque. So both the weight of the mass and the weight of the pole are going to generate clockwise, and the vertical component of tension, since it pulls up on this position, is going to generate counterclockwise.
Okay, so it's technically like where it's pulling.
Yes, like where it's pulling in the direction it's pulling kind of contribute to the direction that single force would try to make it spin.
And those two would be the same direction, but one is negative?
Correct.
Okay.
So, well, I guess you could think of it as 5 meters and negative 5 meters to kind of reverse the direction if the fulcrum is 0.
Okay.
Does that address the
Yeah.
concern? For this type of question, it is always complete. Well, sometimes what I would do, and this is something you can do in the middle of the test, it's fine, is to take just your writing tool, hold it kind of like the object, and then physically push on it in the same direction as any given force, just to check what direction it would make it spin in.
That helps a lot, actually.
Bless you. Yes.
On question 11, for part B, when you're finding the true pressure, are you just like adding the like 1 atmosphere equivalent?
Correct.
Okay.
So on planet Earth, the term true pressure, which is really just a vocab term, refers to the true pressure and absolute pressure are synonyms, by the way. I may have used them interchangeably at some point. And that's just a vocab word specifying the total amount of pressure acting on something given where it is, including the atmosphere. And going underwater doesn't get rid of atmospheric pressure, it just adds the water pressure on top of it. So part A is calculating just the water pressure alone at that depth. And then part B is adding the atmosphere to it to find the true total absolute pressure at that depth. Now, admittedly, the water pressure down there is way more impactful than the atmospheric pressure. Like, you could remove the atmosphere and you'd still be the same level of dead. But technically, that would be the total amount acting at that depth. And again, going underwater doesn't get rid of the atmosphere because the atmosphere is pressing down on the surface of the ocean. The only way to avoid atmospheric pressure is to leave the planet, and then you have different problems. Now, sometimes I will say, just ask you for like, what is just the water pressure? I will make sure that it is stated like that. If I say just water pressure, then this formula for A gives you exactly that answer. Yes.
So are we gonna have to know, just like write down somewhere that the atmospheric pressure is that?
If you ever need that information, I would include it within the question. But it is totally fair game, just for emergency's sake, to put this conversion on your formula sheet. 1 ATM is 101,325 pascals.
Because it wasn't included in that problem.
Ah, yes, sorry. But again, the practice test is meant to be more difficult. But, let me, in the interest of fairness and absolute information disclosure, let me check again on the actual test. Okay, yes. If it is needed on the test at all, it will be listed on the test. Yes.
Okay, question, 10 part B. We, like, used the, total, total P I equals total P Z. How come for part B we couldn't use kinetic instead
You
of-
could. You totally could.
Okay,
You could use conservation of kinetic energy because part B is an elastic collision. I just prefer not to.
okay, alright.
Because if a collision is perfectly elastic, not only can you use conservation of kinetic energy, this one also becomes a valid starting point to compare the colliding object's velocities. And it's based on the conservation of kinetic energy.
And they gave you the same answer?
Mhm.
Okay.
Yeah, there's 3 starting choices for elastic collisions, and I tend to just choose the 2 that I prefer.
Okay. Thank you.
Welcome. Bless you. How you guys feel coming into this week?
Great.
Yeah?
Mhm.
When we were doing like the cylinder problems, like there's a certain amount of like mass, I guess, on one side and you have to like calculate the force.
Mm-hmm.
Do you always calculate the area for those? Or like if it tells you the area, can you just, like, I'm kinda confused about when to use what.
Hold on, are you talking about this?
Yeah.
Okay. Now, in the interest of, again, absolute useful information when possible, this isn't technically on the test. As I was writing it, this just didn't end up being on it. Now, to answer your question, if you were doing a problem like this, and there is 1 or 2 maybe on the homework, you very specifically need the surface area of the round part of the piston. So if it gives you radius, you would have to calculate area, just area of the circle. But this didn't make it on the test.
I just wanted to make sure.
No.
that would-
These are the types of questions I want to answer today. And all this week.
force of centripetal equal the force of gravity?
In an orbit question, yes. And for context, let's scroll up to an example of what I mean by that. The rules for centripetal force is that some real force has to play the part of it. So in addition to the formula for centripetal force, it by definition needs to equal something else. So centripetal force is equal to mass times velocity times orbital radius, or the other formula, there's a second option. And whatever the situation is, centripetal force also has to be caused by some other specific force. Something has to act as this. So in the case of swinging something by a rope, it would be the tension in that rope, and you might have some other way of figuring out what that tension is that you could set equal to this. But if it's an orbit question, which if something is orbiting something else in space, the explanation for that is always gravity. Gravity would always be playing the part of the centripetal force in that case. Because gravity is what causes orbital motion in space, because there's not really anything else in the vacuum of space to cause that sort of thing. So the general rule is something always has to act as centripetal force. Therefore, something will always be equal to it. If it's tension, tension goes in that place. But in the case of space orbit, which again, there will be a space orbit question, gravity has to play that part, because in space there's nothing else present. Gravity is one of the only things that travels through the void. So if it's an orbit question, and again, the question will always be written from the perspective of something is very clearly orbiting something in space, like a moon around a planet or something like that. In that scenario, gravity is acting as the centripetal force. So this is the main starting point for an orbit type question. An orbit happens because the two are equal in that scenario. Does that answer the question?
Yeah, but I thought, like, what about the formula FG is mass times gravity too? Is that also equal to the force of centripetal?
So that would only be true if the object was near Earth's surface. So to kind of talk back about the universal law of gravitation. So throughout this course, there have been two ways we've calculated force of gravity. Initially, we did mass in kilograms times negative 9.8, but in the last couple weeks, we also talked about the universal law of gravitation, which is just the name of this formula. And this is how you calculate gravity anywhere between any two objects. This only works on Earth's surface. G, that negative 9.8, was basically derived from part of this formula, and it just tells us what the acceleration of gravity is only on the surface of planet Earth. That number stops being true if you are not specifically on Earth's surface. If you go too deep or go too high up, that number starts changing. So this would only be what you put equal to centripetal force if gravity is causing centripetal motion on Earth's surface, which isn't impossible. I gave a question in lab actually where gravity was acting as a centripetal force on Earth's surface, but it's just not what would happen in space. Because in space, once you're too far away, that 9.8 stops being true. Just for context, at the height the space station is, that acceleration has dropped from 9.8 to 8. Run a board real fast. So for scale, Earth and Moon are very far apart. That's why getting to the Moon is hard. And the space station would be there, that dot. And that high up, gravity drops from an acceleration of 9.8 to an acceleration of 8. So that high up, gravity is dipped by about 10%, give or take. 20%? Yeah, 20%. So, takeaways. This only works if you are touching Earth's ground, and even then it still fluctuates. If it's in space, you have to use this because the objects are too far apart. And I may even give you objects that aren't planet Earth, because you could use this for the Sun and Neptune if you wanted to. As long as you knew the Sun's mass, Neptune's mass, and how far apart they were. So, this is just a highly specialized version, simplified down just for the weight of objects on Earth's surface. This is the general rule that applies anywhere in the universe. Does that answer the question?
Yes.
Okay. Additional context. That high up, gravity is still like 80% what it is on Earth. There is gravity in space. The astronauts are only weightless because they're constantly falling. And even this far out, gravity still exists. It's just a lot weaker. Like, it's still there. Gravity doesn't turn off. It just gets weaker and weaker. Technically, there's gravity pulling you towards Pluto right now. It's just too weak to notice. You gave me an idea. You guys can keep pondering and looking for questions on your own. I'm gonna try to calculate something real quick, just for fun, because when you're a physicist, you do math for fun. Okay, so again, if you're orbiting, gravity is acting as a centripetal force, and if it's you know, planets and moons very far apart, this isn't true anymore. But it would be true if you were orbiting around the Earth at a height equal to Earth's surface radius. So this would only be true if you were orbiting at the ground level. And so hypothetically, if you were orbiting at ground level, you'd just be running around the surface at super speed or floating just above Earth's surface while moving at super speed. So what I did here is I just tried to figure out how fast you'd have to be moving to orbit Earth at the surface where this would represent the strength of gravity. So I set centripetal force equal to Earth's surface level of gravity, and for R I used Earth's surface radius, so this would be your distance from the core on Earth's surface. And in order to orbit the Earth at the level of Earth's surface, so either running at super speed or hovering above the ground at super speed, you'd have to be moving at 7,901.63 meters per second, which is approximately Mach 23. So even if you could move that fast, you'd probably destroy the planet from all the sonic booms you're creating. Which is kind of one of the biggest paradoxes of Flash, honestly. Like, one, where does the energy come from? Because it's definitely not from the food he eats. I know it's the Speed Force. Two, how does he just not create all of the sonic booms whenever he does anything? Like, that's probably the biggest break in physics with speedsters in comics. They would destroy the planet if they created sonic booms accurately. So his real power is somehow not transferring energy into the air when he doesn't want to.
You said that you could find tension and then set it equal to that.
Yes, that would be a scenario like this, where tension would be acting as centripetal force right now instead of gravity, because it's the rope forcing this thing to move in a circle. So some real force has to serve as the centripetal force, and if it's a physical rope, it's going to be tension.
So in that situation, can you show like how the formula like would change compared to
Yeah. Well, I suppose one of the issues with if tension is acting as centripetal force is that there's not a dedicated formula for just tension, but there's an example from the centripetal force notes that I just didn't do in class, just didn't fit into how the lecture structure wound up being on those days. Sometimes I write more examples than I need. So I'm going to dig that up real quick to kind of demonstrate. That was chapter 6. Oh, chapter 7. Again, if you were looking at the notes slide, this one was in there, but we just didn't end up doing it within lecture properly. This is an example of when tension would act as a centripetal force. I've mentioned that ye old slingshots, not the rubber band kind, but literally the stone in a sling kind, use centripetal force to cause the stone to accelerate and then fly off in a straight line. rock, sling, orbital radius of 35 centimeters. Stone's mass is, did I mention the stone's mass? Yes, I did. It's 300 grams. And there would need to be some tension in the ropes of the sling in order to cause this to happen. If there was no rope tension, then there's no force drawing the stone constantly to your hand, and then the rock just flies off in a straight line. That's why if you were using a device like this, you spin it up until it's at the speed you want, and then you wait for the right moment to basically just let go. So once you let go, tension stops and the rock moves in a straight line as it wants to. But as long as you're holding it, there's gonna be a tension between the stone and your hand, and that's gonna be what acts as a centripetal force on this object. Now, tension itself does not have a dedicated formula because it is a type of force. It is a force that can act that happens to be caused by the ropes in this example. And we actually know that the stone's launch speed is 50 meters per second. So in this particular question, we actually have all the information needed, because we know the rock's mass, its orbital radius, and its launch speed, to determine, like, calculate what is the centripetal force, and that would be the tension in the rope. So this type of question kind of admittedly changes it a little bit. Here, you have everything you need to calculate centripetal force, and then tension would be the centripetal force. So if I asked you for tension, you'd find centripetal force, and then tension would be that number.
Okay,
So slightly different genre of question.
okay, thank you.
You're welcome.
And the first two questions are literally just like conversions, right, between linear and angular.
Correct. So part A, determine linear acceleration. The rock's sped up from 0 to 50 in a 1.5 second time span. So A equals delta V over delta T. Solve for linear acceleration. The angular acceleration would then, you could then convert the linear from the first part into angular for the second part. This next part is a third acceleration, that being centripetal acceleration. And AC is V squared over R, so just a third acceleration to solve for. The point being, all three types have a different number, weirdly, because they all represent different things. You know what, let me actually work that to show, rather than just hand waving it. So first up is linear acceleration, delta V over delta T. Final speed is 50, initial speed is 0, speeds up over a 1.5 second timetable. I think that's about 33.3 repeating. Yeah. And that is the stone's linear acceleration as it speeds up. That's the rate of change of its linear speed going from rest to top speed. Then alpha is the angular acceleration, and my intended way to find that would just be to convert linear into angular using the radius of the sling. So that would make alpha equal to A over radius, 33.3 repeating, divided by 0.35 meters, and alpha would be 95.24 rad per second squared.
So again, measuring a different thing, that's the increase in its rotational speed, so how fast it goes from not rotating to rotating very quickly. And then the third type of acceleration, centripetal. This is a measurement of how, it helps you find how much centripetal force is needed to cause this to happen, and in this particular case, it'll also tell you how quickly the stone's direction is changing every single second. There's two formulas for AC. I've largely been using them as a part of the centripetal force formula, but you can calculate centripetal acceleration by itself. Sorry, I'm gonna try to write it more like a normal English A. My handwriting is just all over the place today. Is that clearer? English A, Greek alpha. So English A with a subscript C is centripetal acceleration. It has two formulas. Since we know linear speed, I'm just gonna pick this one. 50 squared over thank you. And this will give you the biggest number yet. Required centripetal acceleration of 7,143 approximately. And this tells you that the stone's direction is changing a lot every single second, because it is lapping around your hand very quickly over a fairly short radius. 35 centimeters is not very big. And it takes a big acceleration to cause its direction to keep changing, to keep it in that circle. So part of this example is to illustrate that all three of these forms of acceleration represent different things. Change in just linear speed per second as it's speeding up to that point. Then change of its rotation every second leading up to that final point. And lastly, its change in linear direction caused by the centripetal force, making it move in a circle. So they all mean different things. Lastly, what is the tension required to spin the rock? Since centripetal force is acting as tension, you can use centripetal acceleration to find centripetal force, and that would be the tension number. T equals FC equals mass times AC. So 300 grams or 0.3 kilograms times that very big acceleration is going to give you a required centripetal force of somewhere between 2,000 to 3,000 newtons. Yeah, about 2,142 newtons. Which is to say, it would have to be a very strong sling and a very strong swing arm to make this particular feat happen. It also means the sling is made out of very durable materials to not snap. It can handle a tension of over 2,000 newtons. How you guys feeling?
Will the conversion factor of rotation and radians be given to us on test?
Yes, if it is required, it'll be listed within a question. Let me double check that real quick. Make sure that that's in the draft. All right, thank you for reminding me. There is a question, I had to add that. I need to add that too. Alternatively, I'll put it on the board and it will stay there all week. So, thank you for reminding me. In fact, I'm gonna do that now before I forget. One rotation is 360 degrees, or alternatively, 2 pi radians. And that will just live there for every section of the test. You know what, I'll also put pressures and atmospheres too. Pascals and atmospheres, excuse me. I don't think I put like miles in here. Alright, that should be every conversion needed. You do have to remember like the metric prefixes though, but no, you know what, why not, just for convenience sake. Anything else on your minds for right now? Alright. We're all here for today. Please let me know any questions you have while you're studying. Again, lectures this week will be entirely review focused or random question focused, whatever you have in mind. So, whether you take a test this afternoon or not, let me know if you need anything. I think you guys are going to be great, and have a great day.